Okay, so I'd like to just welcome everybody for the third lecture. So before I make a formal introduction, I'd first like to just thank Louisa and Bob Fernholz. The Fernholz have been just tremendous supporters of the math department, directly and through their foundation, the Fernholz Foundation, and in particular their foundation is us to have the Minerva lectures and Farb. So Professor Benson Stanley Farb of the University of Chicago grew up in a small town outside of Philadelphia, Pennsylvania. After graduating from Cornell, he went to Princeton. Wait, this is ridiculous.
Yeah. How did you know? Yeah. We went to rival high schools. He was like 30 years ahead, but yeah.
Look, this is Benson's third lecture. By now, everyone here in the audience knows that Benson is a brilliant mathematician. Mathematics is beautiful, interesting, and further, he's a gifted expositor. That from his lectures, they're not only enlightening but inspiring. So this is stuff that. Oh, right. So Benson's a really good guy. He cares about things very much, and he thinks about them deeply. And part because of that, the MSRI is whole topics workshop. And what that meant was that we looked at Bill's published and unpublished papers. But we ran into multiple roadblocks. Benson was just totally valuable for enabling. So actually, I need to say it was just such great to be able just to out with. So I'd like, please welcome Benson Farb for third.
Thank you. Thanks, Dave. If my mother had still been alive, I would have assumed she'd forced you to say all that. But I know that wasn't true, so it really means a lot. Thank you. Thank you. And I want to thank everybody for coming. I want to thank you for the lectures. I want to especially thank Peter Sarnak for being a great host. And this is all today also joint work with Eduard Looijenga, and it's based on this paper, and that's the title of the talk, The Nielsen Realization Problem for K3 Surfaces. There's Eduard. And today I want to talk about finite subgroups of mapping class groups of K3 surfaces. I will define all those things, but I want to start out with the Nielsen Realization Problem, which was posed in the 1920s for surfaces, meaning real two-dimensional surfaces. So you have, I'll just remind you, have don't worry about orientation, but it's orientation-preserving diffeomorphisms. In dimension 2, the definition of mapping class group is a little different than I gave in 4. You just do orientation-preserving ones, and you have a map to the mapping class group, which is just the isotopy classes. So it's pi naught, it's the isotopy classes of diffeomorphisms. And the Nielsen realization, Nielsen asked, and the Nielsen realization problem, given a finite group, you can ask this for other subgroups, and people have since, but he asked, given a finite subgroup of the mapping class group of a surface, when is it, so G? One way to say it would be you have a section of pi over G. When is there a section of pi over G? Another way to say that is when, is it realized by a finite group of diffeomorphisms? And by realized, I mean you have a group, and each element lists, it's a representative for each class. And this is not trivial even for cyclic case, when G is cyclic. And what it's asking is, if F is a diffeomorphism and F to the D is isotopic to the identity, does there exist a G isotopic to F such that G to the D equals the identity? And Fenchel solved this in 1940. And it's in my book with Dan Margulies, which you should buy, a primer on mapping class group, that proof. It uses a completely interesting idea because it doesn't occur on the surface. And let me just point something out, though, essentially due to Riemann in its uniformization theorem. G is realized, he of course wouldn't say it this way, by a finite subgroup G contained in the diffeomorphism group of a surface, if and only if, and this is all following from the uniformization theorem, G is realizable by a finite subgroup of isometries of the surface in some metric, I'm going to phrase it, where the curvature of the metric is -1. So hyperbolic. If your G is at least 2, every surface emits a hyperbolic metric, it emits a whole space of them. And you want to know, and to prove that these are equivalent, you just say, if you give me any finite group of diffeomorphisms, you take any metric, you average it under the group. It's finite, so it makes sense. And now the amazing, and you have some metric, and G is acting by isometries, the uniformization theorem says there's actually a diffeomorphism, it's even quasi-conformal, that conjugates this in diff to a constant curvature metric. So the conjugation of the action will realize the diffeomorphism. But equivalently, it's the same thing for the automorphism group of a surface endowed with a complex structure. It's just because the group of complex automorphisms is the group of isometries because it's true for the universal cover. That's the magical thing, that those two groups are the same. They're both the Mobius, the group of Mobius transformations. And finally, in 1983, another student of Thurston, who we just talked to, Steve Kirchhoff, proved the Nielsen realization problem is true. All finite groups can be, for all finite groups, they can be realized. So there's 3 types of problems, like a metric version and a complex version, but they're all equivalent by what I just said, by Riemann, for all finite G in the mapping class group. And proof cartoon, and this really goes back to Fenchel for cyclic groups. And Fenchel did it with topology. You take a space, I'll call it Tyche sigma G. It's the space of constant curvature -1 metrics on the surface. And you mod out by kind of changing coordinates the connected component of the identity, which I'll just remind you, the mapping class group, it's the same thing as diff mod the connected component of the identity. I'm gonna write it up and down in a random fashion. This is some space. It turns out this is, see, it's diffeomorphic to r to the 6g minus 6. It's actually a amazingly a bounded domain in C to the n. But the mapping class group acts on this thing properly discontinuously. And so you have a finite group action on Rn. Now, if you have a finite cyclic group, purely topological, acting by homeomorphisms on Rn, it has a fixed point. But in general, so this is number one, to find a fixed point. And then it's a metric, so I'll call it sigma g comma the metric, and then you interpret that G can be realized, G twiddle, this group of diffeomorphisms. Not only can G be realized by a group of diffeomorphisms, but G can be realized as a group of isometries in that metric. So because he knew already these are equivalent, everybody knew its Nielsen realization is equivalent to finding a fixed point for a finite group action on Teichmuller space. You need something geometric. It's not just true for a general finite group. It is true for cyclic, and that's how Fenchel did it. If Teichmuller space had some kind of negative curvature, it would be standard. And yeah, there's a whole story, but I'm just gonna, that's the story in dimension 2, and that's what I was like coming into this with. And I'm gonna kind of tell you the story of discovery. Okay, any questions? I just want, this is sort of a background understanding. In our big picture in this lecture series, Thurston gave us a kind of picture of, there's like 3 big different types, sort of corresponding to a kind of Jordan decomposition, a kind of unipotent type, semi-simple with infinite order, and finite. And in these talks, I'm talking about these elliptically fibered 4 manifolds, and K3 surfaces is a special case. And we're only doing the kind of elliptic and parabolic types, or unipotent. We're not doing the richest, maybe, semi-simple type, but this is already telling a whole story.
How important the finiteness?
Oh, for this? Oh, yeah, it's known that there's no section. Morita proved there's no section of that whole thing, so it becomes an interesting question for different groups. And some people have done a lot of work on that. So let me just talk about, today I'm just going to talk about K3 surfaces. I'll tell you why. We're focusing in on like a key case in 4 manifold theory. So really quickly, definition, a complex surface M is K3. This was named by Andre Vey after Kodaira, Kummer, and Kaler. A complex surface M is K3 if 2 things. There exists a holomorphic 2 form on M that's nowhere 0. Okay? Well, here's an example of that so far. I can take a complex torus and take dz1 wedge dz2. Right? That descends, it's invariant by translation. That's a form on C2. It descends to a holomorphic 2 form. It's nowhere at any given point. It is not the 0 form. Literally, it's not the 0 form. So right now we have complex tori, but I'm adding the second condition that you're simply connected. You might say, what in the world? These are sort of random conditions. Kodaira has a kind of classification of compact complex manifolds. There's the analog of like the 2 spheres, genus 0, the torus is genus 1, and then higher genus, and they behave differently. And I won't go into the whole story, but there's like the rational guys for minimal surfaces, but there's a classification. And this sits in the classification, there's the kind of genus 0 case, which is essentially complex tori, but then this new thing appears that doesn't appear, these K3s. They're essentially it. There's small variations. So this is like the simplest of the complicated examples of algebraic surfaces. It's like at a phase transition, and that's why there are literally more than 10,000 papers on these. And it's crazy, crazy rich. So that's what we thought we would start with. Okay, so that seems like a weird thing. Just from that, let me do a side comment. This implies that the second homology, equipped with its intersection form, this is non-trivial, this is Hodge theory, but no other conditions, and the adjunction formula, it is isomorphic, isometrically isomorphic as a lattice to the negative definite E8 lattice, this crazy thing, and then the hyperbolic plane. And I'll just say, this is sitting in, so yeah, sorry, okay, so that's a lattice. It has signature 319. And it has an orthogonal group. It seems sort of random, but it's really a very profound thing. And let me just give you some examples. And this is my favorite thing. Examples of K3s look totally different. One is any smooth quartic. So you take the 0 set of a degree 4 polynomial in CP3. So, for example, the vanishing locus of x to the 4th plus y to the 4th plus z to the 4th plus w to the 4th equals 0. That's called the Fermat quartic. That's sitting in CP3. That is a two-dimensional complex manifold. Okay, any questions? And it is not obvious, but you should try to work it out. It actually satisfies these two conditions. You should know the Lefschetz hyperplane theorem, but I think you can do this one without anything else. Oh, what are some other ones? I'll just give you a degree 2 branch cover. You take CP2, and you take a curve of degree 6. I'll call it a smooth curve of degree 6. And you take a 2-sheeted branch cover. It's a K3 surface. There's a whole space of these, because there's a whole space of degree 6 curves. Let me just give 2 more. Oh, M2 from yesterday. In other words, you can take the rational elliptic surface, this blow up at 9 points of CP2. You have this elliptic fibration, and then you pull it back by z goes to z squared. And that's a K3. These seem like random constructions, but this is an absolutely fundamental class in this classification. And they come up everywhere. And in fact, Hamilton didn't know it, but when Hamilton was studying, Hamilton, I mean from the 1700s, that Hamilton. He was studying, Jesse Wolfson went back and read his papers, and he was working on K3 surfaces. He didn't realize it, of course, but it's amazing. They really are natural. So there's that. And 2 more things I want to say. I'll just say this. The intersection of a degree D smooth hypersurface in CP4. So it's the intersection of 2 3-folds. So degree 2 3-fold and a cubic 3-fold. A quadric and a cubic 3-fold. Intersection is a K3. And finally, I want to do one more. If you give me a complex torus, C squared mod a lattice, so you think of C squared as R4, you take 4 linearly independent vectors. And then you take the group of translations generated by these vectors. The quotient will topologically be S1 to the 4th power, S cross S1, but it'll have a complex structure because C2 does, and the translations preserve the complex structure. And there's a construction where you take, I'm going to do it the topologist way, so please forgive me, algebraic geometers. So you can take, there's an involution, ZW, so I'll call it I, goes to minus Z minus W. It's an involution on C squared. It's an involution on A. So it's a group, so I want to take A mod that, but it has 16 fixed points, namely the set of 2 torsion points. Think about it. If you have, just for a torus, the square torus, you have a half I over 2 and a half plus I over 2. You're a group under addition, when you modulo translation, each of these is order 2. You have 4 two-torsion points, right? And under an involution, if z goes to minus z, what's a fixed point? It's when this equals this, so 2z is 0. And there's 4 on this, so there's probably 16 on this. Okay? And so what you do is you blow up at the two-torsion, you blow up at 16 points. A of 2, this abelian surface, and this is called the Kummer construction. And then you mod out by the group generated of this involution. Now, it's still not acting freely, but miraculously, this is a K3 surface. It's a manifold. Okay, and it gets a complex structure with it. So any questions? And I should say, many of these are not algebraic varieties. But, oh, yes, here are some, these are the real points of some K3 surfaces that I pulled from the web. Okay, these are each one of these is its own little world. Right, these constructions come from like kind of very different things. And the remarkable fact, which is not explicit, you can make some abstract moduli spaces of complex K3 surfaces. And Kodaira proved in 1964 that that space is connected. And as a consequence, you get all K3 surfaces are diffeomorphic to each other. It's really hard to see that. And there's a whole bunch of questions to try to see it explicitly that like no one's asked just because, you know, just different points of view, different kind of field. But it's really great. And I mentioned this yesterday. Each different kind of construction gives us a different lens through which to find finite subgroups or different subgroups of mapping class groups of K3 surfaces. And so let me talk about the Nielsen Realization Problem for mapping class groups of K3 surfaces. So M will always be the K3 manifold, I'm going to call it now, because it only depends on the smooth structure. But each different complex structure sort of exhibits different kinds of symmetries. And there's some amazing, many, many miracles and new phenomena that happen. And so, firstly, in terms of the mapping class group, so pi naught of diff, you have the representation on homology that takes just a class to its. So this is sitting inside, this is the automorphism group of this really cool lattice. That's very complicated. But when you tensor it with R, this thing here is a real semi-simple Lie group, isomorphic to O319 of R, if you know the names of semi-simple Lie groups. Okay? So it's an arithmetic subgroup. It's a cofinite volume discrete subgroup of a semi-simple Lie group. And Borsea and Donaldson's thing is much harder, but they proved Donaldson proved, anyway, together they showed that the image of rho, you can't get all the orthogonal transformations. You can only, the image is, I'll call it plus, where this thing is some kind of a spinor orientation. And what I mean by that, you can imagine this thing acts on something natural. And it acts on the Grassmannian of 3 planes, of positive definite 3 planes, right? You can look at this 22-dimensional space, real vector space. It has this quadratic form on it. Some 3 planes are positive definite, some aren't. You look at the Grassmannian of positive definite 3 planes. I'm just going to write it GR3 plus, but it's in 22-dimensional space. And this group acts,
Just to clarify here, mod M is bootmapping plus group?
Yes, it's the smooth, like what I did before. It's pi naught of diff.
Sorry.
Yeah, I'm just claiming what the image is. What the two people did is Donaldson said this amazing fact that there's some spinor orientation. It's some, just for experts, there's a tautological three-plane bundle, and it has this canonical orientation on it, and he showed that any diffeo has to preserve that. But there are some of these, one of these doesn't, half of them don't. So he showed containment, and then Borsea just exhibited enough monodromies to show surjectivity. We still don't know injectivity. Definitely don't know. Yeah. Yeah, I mentioned this yesterday. These are isomorphic. If this is the topological, it's isomorphic by Friedman to the whole thing. So, okay. So good, it's index 2. But now I want to talk about finite subgroups of the mapping class group and the Nielsen realization problem. Yes? Oh, sorry, can you repeat that?
So we have all K3 surfaces.
Yes.
Why are we?
The complex structure, that's right. It's a big C, and there's an amazing mystery, amazing to me, is that somehow the typical K3 we know has a complex structure, and floating in this C is like a codimension one spaces of like algebraic ones that are 0 sets of polynomials, and nobody can write down, except for the Kummer construction, as far as I know, nobody can write down any complex K3. Because it's only kind of like a bunch of obstructions and of cohomology groups, and then you deduce there exists locally, and you know what I mean? It's not a direct thing. So I think that's a great mystery. I don't think anybody's thinking about a construction. I just feel like there's some smart Princeton student who will just go, here's the 15 dimensions worth of, or the 57 dimensions worth of K3s, and just you construct 57 dimensions worth, and that's it. I don't see a reason that couldn't be so, but I don't think anybody's thought about that. And to me, that's like a great So 2 things we know, some very deep work that I'm going to use. For all complex K3s, they're all complex structures. I mean, all K3 surfaces are complex, have some complex. I mean, the K3 manifold, it's one manifold. So I mean, for every complex structure in a K3, every complex K3 surface is scalar. There's always a compatible scalar form. And then Yao proved a remarkable uniformization type result is that for all Kähler metrics, for all Kähler classes, there exists a unique, so a Kähler metric, it has a complex structure, it has a metric, and it has a symplectic form. And that symplectic form gives a cohomology class. Okay? And so Kähler metric, it's just relating these 3 things. It's like, it doesn't matter. If you don't know it, you're not going to learn it now, I guess. But it's like, it's this great thing relating a symmetric and a skew-symmetric form. But there exists a unique Ricci-flat metric. So I'm going to write it as the K3 manifold together with a metric little s, and it just means that the Ricci curvature is identically 0. If you don't know what that means, that's okay. That's the analog. It's like the average of the sectional curvatures. So the Ricci, you plug in one vector, and in each direction you get a number. And that number is to sort of average all the 2 planes containing that vector, the sectional curvatures. So this is a very difficult and deep theorem, and nobody knows, again, as far as I know, what these metrics look like in any way. But they're these miraculous things that I'm going to use. And they're all unit volume. It's only unique because otherwise you could multiply it by a constant. Okay? So in terms of the Nielsen realization problem, so remember what we did in real dimension 2, we said, what if you have a finite group of diffeos? And what if you have a finite group of biholomorphic automorphisms? Or what if you have a finite group of isometries in a hyperbolic metric? They're all equivalent. What happens for these? Where now the best metric you can get on a K3 is going to be Ricci-flat. It doesn't have constant sectional curvature, any metric. And so this is a very hard theorem. This is the start of the whole theory, I think, of Calabi-Yau manifolds and stuff. Anyway, so thus, though, if you take a finite group, I'm going to write it like this, of automorphisms of M equipped with a complex structure. By this, I mean it's bi-holomorphic. I'm just emphasizing that it's a K3, the K3 manifold, and this is a complex structure. You can look at the automorphisms. If you have that finite group, and J is a complex structure, you can first quote Su plus Yau plus averaging. Those must be the three canonical things to do in many mathematical problems. Su plus Yau plus averaging. That was a joke, but Su plus Yau plus averaging, you could take any Kähler metric. By Su, there's a Kähler metric. So averaging a Kähler metric. And now you preserve the Kähler class. That's a cohomology class, but that has a unique thing in it. So you permute all the metrics in that class, but it's a unique Ricci-flat metric, and since it's unique, pulling back Ricci-flat gives you Ricci-flat, so it gives you an isometry. It means that G is a group of isometries of M in for some Ricci-flat metric that, like, again, you have to quote Yau, so it's not really explicit. Sometimes people call the Ricci-flat metric Einstein. It's an equivalent definition. And these are called Kähler-Einstein. So it's not just complex automorphism, it's kind of Ricci-flat Kähler metric. Okay? So the three Nielsen problems for K3 surfaces. So you're given a finite subgroup of the mapping class group now. And if you solve it for complex automorphisms, then you solve it for the metric version. So then G realized by diffeomorphisms, a finite group of diffeomorphisms. Okay? But that's a special case of G realized, G sitting inside some isometry group of some Ricci-flat metric. And what we just proved is that that is implied by G is a group of complex automorphisms. So there are three Nielsen realization problems: the complex Nielsen realization, the metric, and the smooth. And from what I said, it's not obvious which are yes. And I'll leave some mystery. One of these arrows, like, does it go the other way? You can ask, does it go the other way? One of them is an open problem, and one of them we prove it doesn't go the other way. So they're definitely different problems. And we're just going to give an example. But let me just give you some examples to give you a feel for some automorphisms of K3 surfaces. You should come up with your own, given that I just gave you a bunch of recipes for K3s. Let me just do 3 examples of finite subgroups. Of the mapping class group. Some of them I'm going to give to you as finite subgroups of complex automorphisms, etc., even algebraic. And one, I'm going to let M be the Fermat quartic, x to the 4th plus y to the 4th plus z to the 4th plus w to the 4th equals 0. And I'm just going to tell you the holomorphic automorphisms, in fact, the algebraic automorphism group, which is the same as the biholomorphic one. What automorphisms can we see? Each one of these, if I multiply by a 4th root of unity, x goes to the 4th root of unity times x. Sorry, otherwise known as, yeah. Anyway, otherwise known as I. Then that's an automorphism, right? it leaves invariant the 0 set, but it moves the points. So I can do that for each of these. So I get a z mod 4z cross itself 4 times, because I can multiply each of these, right? But beware, but watch it, because if you multiply them all by the same fourth root of unity, it's the same thing in projective space, right? It's all projective, so you mod out by z mod 4z. I know this is z mod 4z to the 3, but you can see the action. You can also permute the 4 variables, and you get a semi-direct product. And it's like the irreducible representation of S4. It's like the hyperplane representation, where the sum of the things is 0. So it's this nice group. Oh, whoops, automorphisms of M, sorry, is isomorphic to this group. So this is this group of order 24 times 4 cubed. Okay, any questions? So you can see you can like write equations. This is not the most symmetric equation. I think there's one where you add x, y, z, w, and that has more symmetries than this. Okay, the second one that we saw is a twist about an embedded 2-sphere. I'll call it S inside of M. We call it T sub S, and it's order 2 in the mapping pass group. And so, and in fact, it's order 2 in the orthogonal group. And these all preserve the spinor norm. So any questions? I didn't say it's an order 2 diffeomorphism, right? Okay. And my third example, by the way, how do you know there exists, this has to be self-intersection number -2? Well, in this Kummer example, where I took a torus, and I blew up at these points, and then I modded out by an involution, this z mod 2. You remember from yesterday, these exceptional divisors, these copies of CP1, have self-intersection -1. So hopefully you can believe me that in the quotient, by z mod 2, they have self-intersection -2. So you have lots of these -2 vectors, and you can do these Dane twists. I'm just saying that's an element of order 2. And in fact, in O of HM, I will tell you, if you look at a Dane twist itself, and look at its induced accidental homology, it's great. It's a reflection in the -2 vector, which is the sphere. That's the order 2 element. It's a reflection. Okay. Let me give you one more. Oh, I'm in the middle of examples. Let me go over here. One more amazing example that looks very specific. But it's an example. And by the way, all these like specific little gems, they're the features. They're not, I used to think like, when I started here doing homotopy theory, like, I don't get it. We don't know continuous maps between spheres. Why are you assuming there's like a metric? What are these algebraic geometry people? It's so specialized. It's like, no, there's no good general theorems. So I don't mean in homotopy theory. I just mean the gems are the mathematics. Sorry, let me just give you, there's an elliptic fibration. Remember I talked about that yesterday. So here's there is a K3 surface that has an elliptic fibration, meaning it has a holomorphic map to CP1, so the 2-sphere, with a generic fiber. I should have asked Amy to animate this. Is a torus. And it has 4 fibers that are over here. They're rational nodal things here, like this. It's like a sphere. 4 fibers like that. And these other things are like 5 2-spheres arranged in a chain pattern. I may as well do it. Okay? So these are just the inverse images of points on the sphere. It's all tori except for these 8 points. And here's a cool thing that ends up preserving some complex structure. Rotate that each torus by an element of order 5. I won't figure out what rotation it is. Rotate, see these 4, you have 4 of these spheres like this, but it's a sphere with the north and south pole identified. So I can just rotate the sky, keeping these fixed by 2 pi over 5. But what's cool is, what I want to do is rotate the first two by 2 pi over 5 and rotate the next two by 4 pi over 5. Here, rotate these by 2 pi over 5 and 2 of them by 4 pi over 5. This has order 5, and it's complex structure. And amazingly, it's sort of absolutely unique. I mean, I'll tell you later. Okay, so any questions?
So is there a way to visualize number 1?
Yes, we should talk about it after though. But okay, so I want to start, how to start thinking about the story. Maybe how to start thinking about how to solve these problems. And if you have a unit volume Ricci-flat metric on M, and I'll have once I have a metric, I can look at the 3-plane that is, it's positive definite. I'm going to describe of self-dual harmonic 2-forms. If you don't get all the details of this, if you don't know what these things are, you can still get stuff out of this talk. It's the way of thinking is more important than any of the details, I believe, but there's a Hodge operator once you fix a metric, you have the notion of harmonic. There's a Hodge operator. Its square is, its square is -1, so it's got plus and minus, it's got plus and minus 1 eigenspaces, and so it's the 1 eigenspace. It's a 3-plane. So what you can do is you form, and this is of course informed and inspired by what Kirchhoff did, but this is a thing that of course algebraic geometers did, or differential geometers. You can look at unit volume, the space of unit volume Ricci-flat metrics. Maybe up to like diff naught. That's called, I'm going to put it tight because it's like a Teichmuller space. And you can assign to a metric a positive definite 3-plane that just takes S to P sub S. Okay? But this thing here, so I was in a talk and I learned about this. And this thing here, I knew was the symmetric space for O319 of R. In other words, just like isometries of hyperbolic space, there's this 57-dimensional space. It's sitting in the Grassmannian, a positive part. A Grassmannian is compact. But think about the upper half plane. It's sitting in C hat, it's compact, but then it's this open subset, otherwise known as the unit disk. The same thing here, there's a ball. And it has a non-Poiseuille curved metric on it. That's sort of one of my home bases in math. And it's a complete O319 invariant Riemannian metric. So you just associated to each Ricci-flat metric one of these, and the orthogonal group acts on this. This orthogonal group acts on this properly discontinuously by isometries. It's like SL2Z acting on the upper half plane. Okay? And great. And so I went into Eduard Looijenga's office. He's a kind of permanent visitor at Chicago. And I went after this talk, and I said to Eduard, hey, wait a second. Diff acts on this, right? Diffeomorphisms, and it factors through the action of the mapping class group, diff mod diff naught. So the mapping class group has an action on Teichmuller space. This has an action of the orthogonal group, and it's all equivariant with respect to the representational homology. Okay? So it's this beautiful thing tying together the Ricci metrics and this kind of symmetric space picture. So I said, Farb said, well, G sitting inside the mapping class group of M, you get a G action, or I should call it rho of G action. on this symmetric space. And the curvature of this space is less than or equal to 0. So you have a finite group action. And there's, whenever you have non-positive curved manifold that's contractible, you can do a center of mass argument. There exists a G fixed point. I'm now identifying G with this image. That fixed point, you now interpret, fixed point, it's some plane. Oh no, it's over here. Yeah, it's a plane, P sub S. So I'm going to call this capital P. This is what's called the period mapping, the differential geometric period mapping. And so you fix a three-plane, and then you interpret is that there exists a G-twiddle, a subgroup of isometries in the metric corresponding to that three-plane, realizing G. Does everybody understand like the outline of this proof? Sorry, everybody. We're not going to continue until everybody, no. Okay? So it's the same thing. If you want to find, we're asking a question, when does a group have an invariant metric? You should look at the space of metrics and find a fixed point. And amazingly, you get all this structure for the space of metrics. And so I walk into Eduard's office and say, hey, Eduard, I think we can prove Nielsen Realization Theorem for finite subgroups of the mapping class group. And I had misunderstood the person's talk. The theorem due embarrassingly to Looijenga and Sue did, I think, surjectivity, and then injectivity was Burns and Rappaport. By the way, I'm being polite. I think the person said the wrong theorem. I'm throwing somebody else under the bus. No, but regardless, it's that the period mapping P is a homeomorphism, a diffeomorphism, say, these are manifolds, but onto not the entire symmetric space, but you have to take away for each delta, for each vector delta in our lattice, where delta times delta, for each -2 vector, you get a reflection, and you take the fixed set of the reflection. So the picture is, here's this beautiful non-positively curved 57-dimensional manifold, and you take out these are codimension 3, it turns out, real codimension 3, and you take them out at some locally finite complicated pattern, and amazingly, the space of Ricci-flat metrics is exactly the image, it's injective onto the space minus this infinite union. And the orthogonal group acts on this, and it's permuting around all these things, right? And the number of orbits is the number of orbits of vectors of length -2. And so Farb's proof was wrong, but it's good to be naive because, yeah. Wait, do I need to? Okay, that's the summary. Okay, so I want to tell you our results. But what happened was I said, wait a second. So you do my proof idea, my wrong proof idea. You have a finite subgroup of the mapping class group, or a finite subgroup. Let me just do a finite subgroup of the orthogonal group. And you want to ask, is it realized by Ricci-flat isometries? And you look, you get a fixed point. If the fixed point doesn't lie in the union of these codimension 3, you get an invariant metric. In particular, you realize by a finite group of diffeomorphisms. In fact, isometries. Not always complex structure, I'll mention that, but, okay? But then I thought, well, wait a second. These are reflections of -2 vectors, and I knew that these were represented by Dane-twist diffeomorphisms. So I thought, wait, maybe Dane twists are not realized. That would explain this. So that was the beginning story, and I have to cut it a little short, but let me tell you, we came up with a computable invariant, which I can tell you what it is. So E are the results on non-realization. So let me phrase it this way. I was going to tell you exactly what it is, and maybe I will if I have time, but I want to tell you the results. It sort of doesn't matter what it is, but they're given a finite group of orthogonal transformations, preserving the spin orientation. There exists a computable invariant. It is a sublattice. It's sitting inside the second homology. It's a subgroup of this z to the 22, this rank 22 abelian group with its inner product, with the following property. And let me just say how you start it. It's defined by G fixes some positive definite three-plane. I'll call it Q. Because this previous proof worked. You use non-positive curvature to get a fixed point. By the way, I don't think there's like a linear averaging. I think this is like a non-trivial thing that you take values in this non-positive curve space. But you get a fixed point. That still represents a three-plane. It's just not a three-plane corresponding to a metric. It fixes, so you get a representation of your group into the orthogonal group of that three-plane. And then you do some recipe. You figure out what the representations are. You can have the trivial rep, a cyclotomic rep, the platonic representations, because it's the SO3, it's isomorphic 2. And then you take like the type, I'll just say it in words. So maybe trivial occurs and some cyclotomic occurs. Then so then what you do is you take the direct sum of all the representations in HM of that type, like over the reals, it's all over the reals, and you intersect it with your lattice, and you take the perp and you intersect it with your lattice. It's a little linear algebra thing, and you get this L sub G. And the key thing, it's computable, and let me tell you the results, since I'm running a little out of time, depending on whether or not Dave's time counted in my talk, but I'll try to finish them. Let G be finite group. So let me just say, for people interested, we left open there's tons of stuff to do after this, just for even K3s. But other manifolds, each manifold it's like, oh, sorry, it's a sublattice. It's a sublattice. Yep, you can compute everything about it, like its isomorphism type, and for any given G that you give me, right. It's this little recipe. You tensor with R, you decompose, you look at this representation of the fixed plane, three-plane, and I get, and you list those reps, and so you do have to do rep theory, but only into SO3. And so here's what the invariant does. So we guess the answer from this global picture. It doesn't prove everything. It proves a little bit that if you don't lie in these, but if you lie in these, it doesn't prove that you still might preserve a metric for some other reason. In fact, you need to not just understand a finite group. I said it has a fixed point, but the fixed set, you have to analyze the fixed set of a finite group of isometries of O319R, and then you want to know, does that fixed set hit this? Because I just want some metric invariant. So it gets complicated. That's what this is about. But then what you prove is G is realizable by Ricci-flat isoms in some metric. That's what I think mostly differential geometers fix a metric and study it. We want to know, does there exist some metric with a property? If and only if LG does not contain a -2 vector, a vector of length -2. The -2 is coming from these like reflection things. So by the way, yeah, so, and 2, G is realizable by a complex automorphism, which is stronger. If and only if, well, you need, remember, complex implies you leave invariant a Ricci-flat metric by Yale, so you need that plus the trivial rep appears in L sub J. And I just want to do 2 sample applications. Crap, okay. Okay. Sample applications. And these are, the first thing, corollary is the order 2 group generated by a Dane twist in the mapping class group. Or if you want, this is isomorphic to the order 2 group generated by a reflection in the orthogonal group. Dane twists are not realized by any finite order element, by any finite order diffeo. For people who know Seidel's result that I mentioned, this is just different. Neither implies the other. But it's not realized by any finite order diffeomorphism. And so let me just say, though, something that's pretty cool is that remark, Serafina Lee, my student who spoke here a few weeks ago, proved for, doesn't matter what these are, in fact, the blow up at endpoints for certain of these, for certain, n has to be whatever, certain values, TS is realized by an order 2 diffeo. And what makes that pretty magical is that it has to be global. Because if you can show that in this little neighborhood of a 2-sphere, this Dane twist is an order 2 diffeo, you could stick that in a K3 surface. But that would violate our theorem. So her thing is some global thing. It's pretty surprising. And let me just give 2 results. I will just state these, even if I go like 1 minute over the official time, but it's still under, I will definitely go in under 60 from when I got introduced. But I just want to do corollary 2, and this uses this Torelli theorem in a major way, and I think this is analogous to old work of Piatetsky, Shapiro, and Shafarevich in the algebraic category, but there exists a subgroup isomorphic to A4 in the orthogonal group. So I'm sort of quoting these things. Realizable as isometries of a Ricci-flat metric, but not as any automorphisms for any complex structure. And how do you do that? You have to rig up a group that satisfies 1 but not 2, and that's like a whole bunch of lattice theory and geometry of numbers. And so it's an algebra problem, but then the Torelli group converts it. The Torelli, this period mapping, it's called the Torelli theorem, this theorem here. Okay, and great, and I want to end, great, yeah, so I want to end. I want to say, in terms of the methods, somewhere here, the thing I haven't mentioned, how do you prove that groups are not realized by diffeomorphisms? That's a whole other part of mathematics. That's the theory of finite transformation groups, where I come to you and I say, here's a finite group of order 2. Suppose the Dane twist was realizable by diffeo of order 2, say. Here's a finite group of order 2. It acts by reflection on homology on a K3. Does that exist? And there's a whole part of mathematics, the theory of finite transformation groups. It uses like the G signature theorem. And so that's a lot of stuff in our paper. And I want to end by just saying a theorem about diffeomorphism groups. Again, this is with Eduard. This is about a finite subgroup of diffeos. And suppose, so we know every finite group of diffeos fixes a 3-plane, but suppose G acts trivially on some 3-plane. This is sort of a well-studied thing in the theory of, they're called symplectic automorphisms of algebraic K3 surfaces. So there's a whole literature, some P in So there's a whole bunch of literature on this, and we just looked at it purely topologically, and so it organizes a huge number of papers where people did these case-by-case analyses. What automorphisms are there in different complex structures? Whatever complex structure you have in an automorphism group, it's going to be realized as a group of diffeos. And so I just want to say, then P is in 2, 3, 5, 7, and the group G in diff is unique up to conjugacy. So all I wanted to say is that you look at, in the orthogonal group, you look at the elements of order 5. A bunch of them, there's like 2 or 3 types, but one of the types fixes a plane. That represents it. And any order 5 diffeo of any K3 with that little condition is conjugate to this. And what's wacky about that is a generic K3 surface with a Z mod 5 action on a complex surface. The complex surface has no elliptic fibering, but you're not preserving it, but you're preserving it smoothly because you're diffeomorphic to this, you're conjugate. And so I will now end, and just to summarize my last 2 talks are that there should be like a Thurston structure theorem for, you want to try to find best representatives of diffeomorphisms of different four manifolds. We looked at one kind of example today, one example yesterday. The kind of general case is still open, and very new structures arise not seen in the complex world, like the Mord-Elvay groups and like these groups here. And there should be a rich story for other examples. And a lot of the things that are true for K3s, the opposite behavior is true for these different examples. And that's the work of Serafina Lee. You can go to her webpage. So thank you for your patience of sticking around.
So any questions?
Oh yeah, a lot of, hidden in a lot of this is Hodge theory because we're using this very strong differential geometric Torelli theorem. Oh, but we can't use Hodge theory to rule out certain finite groups being realized by diffeomorphisms because it doesn't preserve any Hodge structure. You know what I mean? There's no complex, a lot of them don't preserve any complex structure. And to me, one of the hardest things in the paper is proving something's unique up to conjugacy and diff. And what's amazing about the example, I'll just say this for algebraic geometers, what we discovered, you take a diffeomorphism of order, this diffeomorphism of order 5, for example, mod out, this is the hardest thing we did. You mod out, you don't get a manifold. You get these like singularities, and like any group of order 5, and you get these like singularities. We like resolve them in a canonical way and build a new Z mod 5Z action on another manifold. And it turns out that when you quotient by these rotations, this is the amazing thing. You quotient, there's a canonical resolution, and the 4 things on the left become the 4 singularities on the right. and the 4 on the right become the 4 on the left. And you do it again, you get back to where you started. So this must be an involution on some moduli space of elliptic fibrations. With this data, we discovered some great involution. And to hark back to my first talk, that moduli space should be like an arithmetic group, and this should come from a commensurator anyway. So it's a little miracle. It was exciting to discover this like order 2 like involution on a, but it plays a key role in determining up unique diffeomorph Z mod 5 in diff. It does or does not? Oh, great.
Sorry, you're giving a...
Of this one. Oh, but I assume you're using the complex, another. There's different versions of Torelli, and you can get this one. There's a complex analytic version, and the original was algebraic. Great. Great.
So the basic idea is to just move the buffer. I just call some uniqueness.
Cool. Can you just put your name so people know where to go, which paper, or at least a few buzzwords that we can Google? A short proof on surjectivity. This is a new proof. Surjectivity of period. That'll be enough for Google.
Well, thank you very much. Are there any other? Yeah.
So in those corollary, how much happens if you
Oh yeah, spin structure definitely plays an important role because it's very, very useful in the theory of smooth group actions on K3 surfaces. And in fact, after our paper, it was generalized by Condit, I'm sorry, I'm forgetting the name, but it was generalized to more like simply connected certain spin manifolds. Sorry, not just simply, but certain spin manifolds.
non-spin?
Yeah, we don't know, yeah.
Okay, so any other questions? Okay, so let's thank Benson Farb for 3 really beautiful instruments.